The first one, it will be presented by Professor Parmalet from Mechanical Engineering Catering University, Clinton, Michigan, United States. And the name of this presentation, it will be Review of at Listed Development in PM Fuel Cell Research with application to hydrogen-powered drones. So let's listen with attention. Please,
Thank you, Mr. Chairman, for the introduction. Once again, the title of this presentation is Review of Latest Developments in PEM Fuel Cell Research with Application to Hydrogen-Powered Drones. This is paper number 200, and the authors are Brandon Day, who is a Kettering University student, Ahmad Purmovahed, a professor of mechanical engineering. Here in this slide, we are looking and the gray layer in the middle represents a very thin polymer membrane which separates the anode side, or the left side where hydrogen comes in, from the cathode side, which is the right side of this picture. So hydrogen molecules come in here in the presence of a catalyst, which is usually platinum. They break down into protons and electrons. The electrons move through wires, some type of a load, which is a light bulb perhaps, or an electric motor powering a vehicle, and they show up on the right side. The protons pass through the membrane, assuming that we have sufficient humidity. And on the right side, the electrons, the protons combine into water. So the inputs into the system are hydrogen and oxygen, which is shown by the blue arrow here on the right side, and that usually comes from air. And what goes out of the system are, of course, electricity, heat, and water. Here's another picture showing you details of flow channels on the anode side, where the hydrogen goes downward, in this case, on the left side, and the cathode side, or the oxygen side, with the air containing hydrogen will move horizontally. And we could see the membrane, which is shown in pink in this case. This is, of course, the reverse of electrolysis. In electrolysis, we use electricity to break water into hydrogen and oxygen. And here is the exact opposite happens. Hydrogen and oxygen combine into water, and electricity is released. One of the main advantages of this system is that there is no CO2 emissions, no NOx, nitrogen oxides, or no sulfur oxides. Of course, if hydrogen comes from a source other than renewable electricity, then there will be indirect CO2 emissions. These are different types of fuel cells, and as we go down this list, the operating temperature goes up. So the direct methanol fuel cell is at room temperature. Focus of this work is the PEM fuel cell shown in green. So there's a low temperature PEM which operates under 100 C. Therefore, the water comes out as a liquid, and HT-PEM means high temperature proton exchange membrane, where we go above the 100 C and water will come out as steam. And then We have alkaline fuel cells, phosphoric acid fuel cells, molten carbonate, and solid oxide fuel cells, which operate at very high temperatures in the vicinity of 1,000 degrees Celsius. Once again, the inputs to a PEM fuel cell are hydrogen and oxygen. The outputs are water, electricity, and heat. The components, the main components are anode, the hydrogen side, cathode, the oxygen side, electrolyte, which is the membrane in the middle, and of course the catalyst, which is usually platinum. Benefits of fuel cells compared to conventional batteries include reduced weight in most cases and increased operation time for machines like drones. Some information on low temperature PEM fuel cells. The catalysts have a lot of room for improvement, and usually platinum is used as a catalyst in PEM fuel cells, but it is quite expensive, and it contributes about 10 to 15% to the cost of the fuel cell stack. But there are companies that are working on catalysts using less platinum, and in some cases non-precious metals like iron, cobalt, magnesium, etc. The membrane also can use a lot of improvement. Nephron is the one that is used commonly for PEM fuel cells, but it requires the right amount of humidity to function effectively, meaning pass through the protons effectively. Here's some research data on high temperature PEM fuel cells. In this curve here, we're looking at cell voltage versus number of hours of operation. So depending on what type of membrane is used, you can see the cell voltage drop rapidly, as is shown in the black curve, using phosphoric acid-based membranes. And you can see much improvement indicated by the red curve. That's for different type of membrane using a mesoporous silica nanomaterial. And on this curve on the right side, we're looking at proton conductivity of the membrane as a function of number of operations. And it is shown that the performance or conductivity drops fairly rapidly with phosphoric acid-based membranes, but once the mesosilica nanomaterial is added to the membrane, you can see that the conductivity does not drop very much with the number of hours of operation. Here's a picture of a drone operating with hydrogen fuel cell. We can clearly see the hydrogen tank below the drone. There has been some work showing that fuel cells, PEM fuel cells, can increase the operation time of drones between 2 to 6 times compared to batteries if the minimum energy required is generally more than 4 megajoules. And the reason is that if you want to add more hydrogen to get a longer range, the hydrogen does not add a lot of additional weight to the drone. But if you want to add batteries, they are usually very heavy. And it's best to use a lot of hydrogen for a longer range. The layout of a PEM fuel cell battery, a hybrid power range for a drone, is shown here, where the voltage is 80 volt DC, and this represents an 8 kilowatt hydrogen PEM fuel cell. Of course, we need an external 12 volt battery as an example just to start the fuel cell. In this picture, there is a DC to DC boost for the voltage to get to 80 volts, and BOP stands for balance of plant. This is in parallel with a lithium polymer battery, which is in this area. BMS means battery management system. And then below is the drone, in this case requiring 10 kilowatt of DC power. And then there's balance of plant, like pumps, fans, etc., that are required to operate the fuel cell as well as the drone itself. Limitations of PEM fuel cells are many. One is the gas diffusion layers, which are shown on both sides. The geometry of flow channels is very important. The membrane itself in the middle, shown in blue, has a lot of limitations. Usually these are very sensitive to contamination, operating temperature, and humidity is also very important. Catalysts are limited by current material technology. Again, platinum is the most common, but it's very expensive. And their fuel cells are inherently limited in their design since they need constant fuel supply to operate. So here we visually see sensitivity of fuel cell to various contaminations. Fuel cells are sensitive to both carbon monoxide, CO, and also carbon dioxide, CO2, which is shown on the right. Could very severely drop the voltage as indicated in these figures. Here we see data for three temperatures: 60 Celsius, which is here, that's a low temperature fuel cell where the water comes out as a liquid. The two in the middle and on the right side are at a 122 Celsius and 160 degrees Celsius. So these are high temperature fuel cells where the water will come out as steam. And the graph shows the overpotential, which is a bad thing. It reduces the useful voltage of the cell. So this is called by thermodynamic irreversibilities. And on the horizontal axis, we see current density in milliamps per square centimeter. And there are three curves on each one representing different amounts of CO2. So the blue curves correspond to 50% CO2, which is a lot. The red one is 25%, and the lowest, the black curve, is 10%. So as you can see, there is significant overpotential when you have 50% CO2 in the system. 0.14 volts, for example, at 400 milliamps per centimeter squared. At higher temperature, for the same current density, that overpotential drops to 0.024, so that's significant improvement. And at 160 degrees C, that increases fairly by a small amount, but to 0.028. So significant improvement as we go from left to right. The overpotential gets smaller very quickly. Requirements for a 50-pound drone, which is approximately 25 kilograms, were estimated to be a minimum of 1.6 kilowatt of continuous power, some of which is going to be supplied by the battery and the rest by the fuel cell. Energy storage requirement of at least 4 megajoules. And these are the conclusions. With current technology, PEM fuel cells provide a very reasonable alternative to batteries for powering drones. In some cases, fuel cells are more efficient and provide much greater flight time batteries compared to
the whole problem with the current fuel cell technology. What their recent advantage is in both low and high temperature fuel cells, and the advantages include making improvement in two main
So thank you, Professor, for your interesting presentation. I will ask to the audience for any. I have one question to Professor. What is the most challenging topic in this research that you can share with us?
The most challenging, there are several. One is the sensitivity of fuel cells to contamination in the field, mainly CO2. And the other one is humidity control. If you don't have sufficient humidity, then we will not be able to effectively pass protons through the membrane, and if you have too much humidity, you could have a layer of liquid water which will be on the membrane, and it would block the flow of protons. So it is very important to optimize the humidity, and that to me is one of the biggest challenges.
Okay, Professor, thank you. And about the dimension, do you think that in the near future you can reduce the dimension of these batteries?
I don't know. I don't have any expertise on batteries, but there are many different battery types that have been suggested and used. And I think it's quite possible to find better batteries for this application, just like the same thing has been happening for other applications like electric vehicles.
Okay, thank you. We will continue in this section with the next presentation that will be remote sensing schema for fault diagnosis for wind turbines, an academic experimental setup. This presentation will be doing in video mode. The author is Mr. Leonardo Acho from Politecnica Universitaria de Catalunya, Barcelona, Spain. So let's listen to the next presentation, please.
Do you have it?
So the presentation of Mr. Leonardo Rajo is already finished. I will ask for you can begin. Thank you.
Thank you, Mr. Chairman. Today I'm going to present my work entitled Optimal Size and Design of a 1.5 gigawatt permanent magnet synchronous generator for an onshore wind conversion system. The outline of this presentation are as follows. First, we are going to give you an introduction about the motivation of this work, and then we are going to go forward with the sizing design process, including the optimal sizing design strategy, the design specification, and the multi-physics model, and of course the optimization algorithm itself. And finally, we are going to give the results obtained and the conclusions about these results and the possible perspectives of this work. As you may know, annual growth rate of wind energy market have reached 10.8% in 1920, with a global installed capacity of 743 gigawatt. It should be noted that more than 95% of this capacity is produced by onshore large-scale grid-connected wind conversion systems. This fact motivates us to consider this particular type of wind conversion systems in this application to design an optimal permanent magnet synchronous generator. So we have basically two types of wind architecture. The first one is known as type D, and it's usually a direct drive wind turbine. The second one is a type E wind architecture, including a gearbox that connect the low speed shaft of the wind turbine to the high speed shaft connected to the generator itself. Usually we have three types of machines used for these particular two types of architecture, which are permanent magnet synchronous generators, doubly fed induction generators, and some invented machine and certain machines are the performance of these two In this work, we are considering this particular wind conversion system that comes with a permanent magnet synchronous generator connected to the wind turbine through a gearbox. Now, for the design procedure, we are using what we call an output space mapping technique. This particular technique is known for its simplicity in putting a multiphasic model for the machine and its accuracy compared to other complicated and time-consuming and resource-consuming methods. I will be explaining the differences between what we are proposing and what already exists in literature to highlight the contribution of this work throughout these slides of this representation. First, we are fixing our design specifications, and then we are going to put in place our multiphysics model, which is limited to only 2 submodels. We are going to formulate our optimization problem, execute our algorithm, and compare the results obtained based on the convergence of the algorithm, and then we are going to validate the result obtained by the algorithm through a finite element validation to ensure precision, and finally we are going to perform an adjustment maneuver to reinforce the accuracy of our optimization algorithm and our optimization process. I will be explaining each step throughout these slides. Now, if you go forward with the design specification, we have basically 2 types of design specification, geometric and electromagnetic. As for the geometric, we are considering a real wind turbine designed by the National Renewable Energy Laboratory and funded by the US Department of Energy, which is the wind-packed baseline 1.5 megawatt wind turbine. This wind turbine actually exists nowadays in wind farms around the world. 3 basic geometric parameter comes with this wind turbine: a maximum stator radius that should not exceed 2 meters, an actual active length fixed to 0.25 meter, and a number of stator slots that is calculated based on this coefficient. This coefficient fixed to 4 is what we call the number of slots per phase and per pole. We are choosing a value of 4 based on a literature review. This value has been proven to enhance and to eliminate the fluctuations in the shapes and the curves of the electromagnetic force and thus minimize the torque ripple. So our wind turbine will have 144 stator slots. Electromagnetically speaking, the design specification are calculated rating point known as the base point. At this point, the machine is supposedly operating at optimal functioning. So as you can see, our rated power and our rated velocity. Of course, we fix also the maximum phase voltage at 3000 volt. This value is obtained from a previous simulation of this particular machine for this using the environment MATLAB Simulink, and of course a maximum DC bus voltage for the grid connection at 785 volt. This value is also taken from another experiment for a permanent magnet machine that was designed specifically for this particular wind turbine. A maximum flux density of 1.5 Tesla to take into account possible magnetic saturations in the machine, and the power factor of 0.8 to ensure a maximum efficiency. Now, if you go forward with the multiphasic model, which is the first step in our design procedure, we have, using this optimum output space mapping technique, we have 2 models. The first one is a chorus one that comes with 2 submodels, an electromagnetic one, an electrical one, and a magnetic one. That is first analytic. It is fast and relatively simple to put in place. The second model is a numerical model based on the finite elements method, which is precise. Throughout our optimization procedure, we are comparing the results obtained thanks to the chorus model, which is less accurate, to the results obtained thanks to the precise model. Based on these differences on the performances of the obtained machines, we are calculating an adjustment coefficient. This coefficient will help us to reduce this inaccuracy between the 2 models and thus ensure that the final machines are really the optimal ones under this design specification and for this particular application. We'll get from the chorus model the main performances, And of course, from the fine model, which is a precise one, we get all the performances of the machine and its design parameters. Now, if you go forward in our chronogram, the submagnetic model is used to determine the no-load flux linkage necessary for the optimization algorithm. In order to do so, the first step is to put in place an initial numerical model for the machine. This will help us to visualize the distribution of the flux line. After this, the next step is to use this distribution to put in place a reluctance network. This reluctance network is then used to put in place an equivalent circuit that will help us to determine the no-load flux linkage analytically, as you can see on this slide. And finally, the final step is to link analytically to what is obtained numerically. And as you can see, between the two shapes, the one with the star is the one obtained with the reluctance network, analytical one, and the one with the straight lines is the one obtained numerically. As you can see, we can say that there is an accuracy obtained between the two slides. Now, the next step is to use the outcomes of the magnetic model and the electrical model. And we are using this submodel to calculate the electromagnetic torque, that is a function of the current density GS, and the copper section at the stator winding SCU, which is at its turn calculated as a function of the ratio of iron in the copper windings, and of course the dimensions of the stator of the machine. We are using an analytical equation to calculate the DC bus voltage that depends on RS, which is a specific resistance that is used to quantify the copper losses in the stator windings. And of course, we are putting in place an analytical equation to calculate the output power and the efficiency of the machine throughout these equations that help us calculate the losses analytically. Now, we are taking these results from the multiphasic models and injecting it into the optimization algorithm. It's a multi-objective particle swarm optimization. This meta-heuristic, it's known for its performances, especially in avoiding what is known as local optimum that may do harm to the results and make it less precise. We have at least 7 optimization variables, which are the magnet thickness, the air gap, the stator slot length and height, the shaft radius, and of course the rotor extending radius, and the number of turn per coils at the stator windings. Then, after the execution of the algorithm, we have 2 objectives. First one is to minimize the losses of the machine, which will help us to enhance its efficiency, and the second objective is to minimize the mass of the machine. As you can see, it's a wind turbine system that is equipped with a gearbox. And this particular type of wind turbines, we usually looking to minimize the mass of the generator, because we are using less pole pairs compared to direct drive machine, and which will help us to reduce the cost and of course to reduce the maintenance and the transportation and logistics costs in case of installing this wind turbine. Now, after executing the machine according to this design criteria, we are testing the machine. If our machine are constructible, then we are using the parameters obtained from the algorithm on our fine model, which is a numerical one, to verify if the performances are met. We are comparing specifically the torque that is expected analytically to the torque that is really obtained numerically. And as you can see, the torque depends basically on the current density, which can be noted in the QX in the park reference, of course, as you can see right here. There is this parameter, the QOSM, which is our adjustment coefficient, calculated based on the difference between the two models. This adjustment coefficient is injected into the algorithm, and the algorithm is re-executed in an iterative way until we have a very narrow gap between the results obtained from the analytical model and the precise fine element model. as you can see in this work, this coherence between the two models is obtained after 3 iterations with adjustment coefficient of 5.2. Now, we are giving the Pareto friend obtained for the first 100 optimal machine. We are choosing the machine A, which present the best compromises between losses and weight. Machine C, that has the less losses, and machine B, which is the lightest machine. Here is the parameters of the 3 machines obtained, of course, thanks to the finite element model. An efficiency of 96% is obtained, which present a very good result for this particular type of application, especially compared to other design procedure for other type of machine. Now, to visualize more results, we are considering the flux links evolution. As you can see, we have perfect shapes with no fluctuation that also can be seen on the electromagnetic torque of the machine, where the torque ripple are minimum, of course the winding current per phase as well, and the induced voltage that has perfect shape and does not exceed the value that is imposed by the specification criteria at 785 volts. Now, as a conclusion to this work, what we are proposing is a fast and precise design procedure based on the technique output space mapping, where we present two submodels, analytical submodels that are fast to put in place, and we ensure a precise result through adopting this iterative adjustment maneuver. Then we have also finite element validation performed on the machine to ensure that our machines are constructible and they are performing as we are expecting with a very good efficiency. However, as a perspective for this work, developing a more accurate course model that include a lossless submodel, a thermal submodel, an additional lossless submodel is very advised to ensure really that our algorithm is operating as it should, and to reduce the number of iteration and to reduce the significancy of the adjustment coefficient. And another step also as a perspective for this work is to use a second finite element software such as Flux 2D 3D to validate the results obtained thanks to ANSYS Maxwell, and of course an experimental validation for a scaled down permanent magnet synchronous generator can also be conducted to validate further this technique. I would like to thank you for your attention, and I'm all ears for any questions.
Thank you.
I don't believe that you have any question in the audience, but I can do a question, please. For next time, it's gently suggestion. You can present in a more quiet way your work. It's not necessary to explain the whole details, okay? It's a very consistent and very good work, okay? So, in the near future, what do you think about what main aspects in your research the manufacturer can use it in order to improve the different kind of equipment that they usually sell? What is the one or two topics of your research that may be approved and spread by the manufacturers?
Actually, there is a part of my work when I consider the electromagnetic and power electronic interface used to connect the wind turbine to the grid. One of my research includes that considering multi-level inverters to do so. I think that 3-level cascade edge bridge inverters are very good to use for this precise scale of wind turbine starting from 1 megawatt. And to reduce the cost of this power electronic interface, if we are using semiconductors that are modeled for a lesser power and we are associating them in parallel or in series, we can achieve the same power while reducing the cost. I think this is one of the axes that a manufacturer can use to improve and to reduce the cost of power electronic used to connect to the wind turbines to the grid.
Thank you for your explanation. See you soon in a new conference.
Joao, there is one question.
Oh, you have a question in the chat. What about electromagnetic compatibility interferences of other magnetic sources? Inside of a wind turbine, there are many electromagnetic noises.
Yeah, thank you for this question. This is true, there is a lot of noise in a wind turbine, but at this particular stage of our work, we are not considering all the factors that might intervene in the operating of the machine, because we are trying to, at this stage, we are trying to provide a design procedure that is fast and quite precise. But in the larger particular work, we are going to include types of noises, other types of losses that may take place to enhance the applicability of what we are proposing. But there is actually a lot of noise in the wind turbine. Thank you.
Okay, no more questions in the audience, no more questions in the chat. Thank you again for your presentations.
Thank you.
So next we'll continue this section with the next presentation, whose name is titled SCADA, Data-Driven Wind Turbine Main Bearing Fault Prognosis Based on One-Class Support Vector Machines. The authors of this research are Mr. Inswasti, Tutik Ven y Vidal from Ecuador University, from Polytechnic Catalonia University, and from University of Marino, Colombia. So let's listen to the next presentation.
Hello everyone, I'm going to talk about offshore paper called SCADA Data-Driven Wind Turbine Main Bearing Fault Prognosis Based on One-Class Super Vector Machines. This paper is created by my partners Yolanda Vidal, Christian Steven, and me, Andres Inswasti. Okay, who am I? My full name is Germán Andrés Inswasti. I'm an electronic engineer from Universidad de Nariño. Right now, I'm a master's degree candidate in electronic engineer. I live in a south of city in Colombia called Pasto. My main research topic is about machine learning, multispectral image, anomaly detection, and object recognition. If you want to know more about me or my work, please visit my webpage andresinswasti.com to see more details. Let's go to see our agenda. First, we are going to see about the introduction, after failures description, methodology, results, and conclusions. So, in the introduction, one of the important characteristics of renewable energies is the support to mitigate the effects of climate change. It is known that there are fewer fossil fuels at every moment. On the other hand, in order to help renewable energies, it is vital to lower costs. That is the reason that this work proposed a fault prognosis methodology to predict the main bearing fault several months in advance. Imagine that to know maybe a failure in months in the future is cheaper than to make a corrective maintenance. Here we have an approach of one wind turbine that we use here in this study. Here you can see the components and the features that is inside of this wind turbine. And if you want, you can see here the more features or characteristics like nominal power, that is 2,300 kilowatts. The rotor diameter is 101 meters. It's a little big wind turbine. That this is to know that it's a real wind turbine that is studied here in this work. Continue to the failure description. The bearing damage and failure can be classified in different ways and use different terminology. You can see here the classification of these failures like fatigue, wear, corrosion, electrical erosion, plastic deformation, fracture, and cracking. Continue with the methodology. This image can show you a very simple way of our technique. First of all, we extract information from SCADA data. After this information is processed by an algorithm trained to identify anomalies and depends on one characteristics, parameters. The classification is anomaly or normal sample. This triggers an alarm to prevent those types of failures. This is achieved by using only SCADA data, which is not created for this purpose. The data is accessible on all industrial-sized wind turbines. Thus, this methodology could be applied to any wind turbine with very low added cost, since the necessary sensors are already installed. Let's talk about our data SCADA. We have a lot of data since January 1 from 2014 to December 12 to 2019. This is a lot of data recorded by every 10 minutes. And we split this data into parts. The first one is the training data, that inside of this train data is only healthy behavior, is a normal behavior. And in the test data exists two types of behaviors. One is a normal data, but another is a failure data or failure behavior, because on June 11 from 2018, exists a report of failure in the main bearing. So our methodology explains that we use only the trained data to identify how is the normal behavior, the healthy behavior, and with this information, this algorithm used to extend this process to identify a failure in the test data and identify also the normal data, the normal behavior. We use two types of variables. The first one is the wind speed, and the second variable is a combination of the shaft temperature and ambient temperature. It's important to note that we use a normalization in these variables to be more efficient in the execution of this algorithm. If we can see in a graphic way this data, you can see here these graphs represent in blue tones the training data and green tones the test data. Here we have the two variables used. Above we have the temperature and below the wind velocity with this with this split of the data. The blue the training and the green the testing. With the data in our mind, how we use this data to train an algorithm? Okay, so the algorithm used here is one class supervector machine that consists in minimization of a function subject to a restriction. This minimization is optimized with every training sample that we have in our training data set. And after we make this optimization, we use a decision function to classify every sample like a normal sample or an anomaly sample. The output of our algorithm is a classification in normal or an anomaly sample. This classification is grouped by month, and we count the amount of anomaly sample classified. So in this example, you can see here for the month month 1, we have an amount of anomaly samples classified, and the month 2 is bigger than the month 1. And we establish a threshold that means that every month is less than the threshold is classified like a healthy or normal behavior, and the months that the amount of the anomaly detection, the anomaly reported is bigger than the threshold, it represents an alarm to be reported. So let's go to see our results. Please have in mind that we use a split of our data. And now we are going to see our test data that inside it has a failure behavior and a normal behavior. And here you can see our results. We have all this test data classified with normal sample or anomaly sample. And we count the number of anomaly sample by month since December 2017 to December 2019. The failure that is reported in this real wind turbine is in June of 2018. And you can see here the amount of anomaly reports in this month. And we established a threshold to identify this failure. This threshold is established by the average of anomaly, the reports of anomaly with at least 3 standard deviation above. That is the reason we established this threshold around 1,000 samples classified like anomaly per month. And you can see here that in April of 2018, the alarm is triggered because the anomaly reports is bigger than the threshold. And the conclusions we have that in this work, a fault prognosis methodology to predict the main bearing fault is stated. It is based only on SCADA data and needs only healthy data to be trained. Other conclusion that is that the proposed methodology works under different and varying operating and environmental conditions. And the third condition is the methodology is demonstrated on a real underproduction wind turbine. The results shown that the alarm is triggered months before the fault appears, thus giving time to the plant operator to schedule maintenance. And thanks. I hope it has been of your interest. Thank you very much. See you.
So it's time for questions. I will ask to the audience. To set the data sample period. Andres.
Hello, can you hear me?
You can read the question in the chat. What
Yes.
are to set the data sample period?
Yes, about this question, it is not a characteristic that we establish. We have data every 10 minutes from the SCADA data, and that is the sample that we use. It is not our criteria, it is only that the disponibility of the data from the SCADA of wind turbine.
For your response,
Thanks.
I ask again for any questions. I suppose that no more questions in this presentation. Thank you, Andres, again, and best wishes for your future.
Thanks.
So we'll continue with the next presentation, whose name is Convolutional Neural Networks for Wind Turbine Failure Classification based on a scattered data. The authors are Poruncajas, Alava, Encada Davila, Tutivan, and Vidal from Facultad of Mechanical Engineering Production Science, Escola Superior Politécnica do Litoral.
Hello everyone, I am Winter Alava, an Ecuadorian student from school, and I would like to present our research work, Convolutional Neural Network from Wind Turbine Failure Classification based on SCADA data, developed by Brian Fruncajas, Ángel Encalada, Cristian Tutiven, Yolanda Vidal, and me. This work was developed under the following outline. First, we have the introduction, which presents the background and important definitions, data overview and preprocess, where the flow of the data preprocessing is described. The CNN architecture, where the architecture and the hyperparameters of the neural network are defined. Section 5, where I present the result. The section 6, the conclusions. Let's see the section 1, introduction. In 2019, wind power met the 15% of the European Union electricity demand, was the primary source of new capacity in the US and Canada, the second largest in China. Failure detection systems are used to provide alarms about the deterioration of different components of a wind turbine, based on different types of information and sensors. The early detection and classification of faults in wind turbines have become essential to increase their competitiveness, since the prevention of faults and timely maintenance reduce the cost of repairs and the downtime of the affected turbine. A SCADA monitoring system uses data that is already collected in a wind turbine controller, and is a cost-effective way to monitor for early awareness of faults and performance problems. This work aims to detect and classify 6 types of wind turbine faults. Since the SCADA data shows the overall health of a wind turbine, it can be leveraged to detect when turbine performance is degraded and identify if a fault is developing. The Table 3 lists and labels all the types of faults that the SCADA system can record. We got labels from F1 to F6, and faults like pitch actuator, generator speed sensor fault, 3 types of pitch sensor faults, and a torque actuator fault. In this work, a deep learning architecture known as convolutional neural network was implemented, which allows executing complex tasks like object detection or image segmentation. For a convolutional neural network to be able to predict, it needs to be fed by training data, so the model can learn in-depth features and patterns, which allows to obtain an accurate prediction. It should be noted that the training data is known for the model, in this case a recompilation of SCADA data of a wind turbine physical behavior. Let's see the section 2, the data overview. The data is generated from a wind turbine simulation model, with variable pitch control and variable speed upline. The main features of the simulated wind turbine are shown in Table 1. The elastic simulation software, FAST, is used to model the wind turbine. While traditionally, the sampling time in a SCADA system is 10 minutes, in this work it is proposed to reduce it to 1 second, using sensors with a frequency of 1 Hz. And to produce more realistic simulation of a wind turbine, wind modeling data generated from wind flow and stochastic turbulence software, TurbSim, is implemented. The inputs of the simulation are at 10% of the intensity of a Cayman turbulence model, logarithmically wind velocity with an average of 18.2 meters per second, and a stiffness factor of 0.01 meters. 260 simulations of 10 minutes are performed. From these, 69 correspond to healthy simulation and 160 to failure simulations, where each type of failure has 20 associated simulations, as shown in the table 3. Each simulation lasts 10 minutes. However, not all this time is used, but only the last 400 seconds to avoid the transient behavior present at the beginning of the simulation. Section 3, the data preprocess. The data is stored in an array X of 90,744 by 9. Such number of timestamp is given by the number of rows, the data. The number of columns is equal to the number of sensor pairs, as shown in the table 2, where we got sensors measure the generator electrical power, the rotor and the generator speed, the generator torque, and the pitch angle for the first, the second, and the third blade, and the forward thought acceleration. The data split process, the previously matrix X, is divided as follows: the 75% for training and the 25% for validation. This corresponds to 69,253 rows for training and 21,493 for validation. The data standardization process reduces the time for training, making the training more efficient. The data is scaled column-wise for the matrix X to be within a specific range from 0 to 1, based with the maximum and minimum values of the training data. The data reshape process, the main goal is to detect the failure in a reduced time of 3 seconds using the available SCADA data. It is proposed to organize the available data from the simulation 3 time steps. This will lead to a detection time of approximately 3 sample times. Transformation is carried out individually for each of the 9 variables. Use a CNN input. As a result, we got matrix B with 3 times 9 columns. The section 4, the CNN architecture of the convolutional neural network architecture. The input matrix of the CNN has a dimension of 1 row, 3 columns, and 9 layers, followed by 3 convolutional layers and 4 fully connected layers. This data passes through the first convolution module. This module is made out by 14 filters, 2 by 2 kernel, with padding and stride equals to 1, resulting in an output size of 2 by 4 by 14, and the second convolution and the same kernel configuration, padding and stride as the first convolution, with an output size of 3 by 5 by 21. The third convolution has 26 filters and the same configuration of kernel, padding, and stride of the first and the second convolutions, with an output size of 4 by 6 by 26. Finally, 4 fully connected layers with size of 350 for the first, 175 for the second, 50 for the third, and 7 for the last one. Note that all these convolutional layers and connected layers have a radio trigger function. The final layer of the network is a softmax block used to squash the 7-dimensional output into a categorical probability distribution. 0 for the healthy, 1 for the hydraulic leak at the pitch actuator, 2 for the gain factor in the generator speed sensor, 3 for the stock value at the pitch sensor of 5 degrees, 4 for the stock value at the pitch sensor of 10 degrees, 5 for the gain factor at the pitch sensor, and 6 for the offset value on torque actuator. The section 5, the results. The figure 3 illustrates the confusion metrics for the validation data. The rows represent the true class, while the columns represent the predicted class. The obtaining overall accuracy performance is 88%. A precision of 100 is reached for fold F2 and fold F6, to a lesser extent for fold F4 with 85.5%, and the lowest precision corresponds to the healthy data. Regarding recall, The highest result is obtained in failure F2 with 100%, the lowest with failure F5 with 51.5%. For the F1 score metric, 100% is obtained for failure F2 and F6. The lowest result corresponds to failure F5 with 65.5%. For specificity, the 100% is obtained for the F2 and the F6 failure, and to a lesser extent with the healthy data. Finally, the conclusions. This work, a promising strategy to detect and classify multiple wind turbine faults, is presented using only conventional SCADA data with an additional high-frequency sample, the sensor with 1 Hz. The proposed method does not require hand-designed functions because the convolutional neural network learns the representative features automatically. A remarkable overall precision of 92.1% is obtained. This result shows that large CNN are promising to develop wind turbine fault diagnosis strategies. Future work will focus on 2 main areas. First, an investigation will be conducted to gain the ability to separate the unknown faults from the known and specific studied fault types. Finally, to face the validation of proposed strategy in a more realistic environment, a downscale real wind turbine in a laboratory will be used. Now we reach the end of the lecture. I thank you for your time and attention. Here you can find our contact emails. And finally, I would like to know if any of you have questions about the presentation. Thank you.
Thank you so much for your presentation. Now it's time for questions. I don't know if there are a question from the audience. Is close to zero in your approach.
Hi, I would like to know which metrics do you refer in your questions?
Let's the V1.
V1. I don't have the response to these questions. I don't think the determinant is a relevant metric or value to be studied. And yeah, that's.
So it's a good topic to discuss in the future. Maybe you can change information with your email. Thank you for your presentation. I hope to see you soon in another conference. Now we'll continue. Calada Dávila, Tutivan Purumcasos, e Vidal from Mechatronics Engineering, Faculty of Mechanical Engineering and Production from Guadalajara, Ecuador, from Control Modeling Identify Application Department of Mathematics, Escalada de Engenharia de Barcelona, from University Polytechnic Catalunya, Spain, and from Institute of Mathematics of UPC Barcelona, Tech, Spain. So let's go to listen to the next presentation. Please. Thank you.
Hello everyone, let me introduce myself. My name is Angel Encalada. I am mechatronics engineer graduated at SPOL. And today with my research partners, Christian, Brian, and Yolanda, I am going to present you our work titled Wind Turbine Multi-Fault Detection Based on SCADA Data via an Autoencoder. The outline we are going to review in this presentation is composed by 5 parts. The first one is introduction, second one is the data description, next we have multi-fault detection model, next we have results and exclusion, and last we have conditions and the further work. Okay, introduction. As we know, to produce a low environmental impact, there is a strong attraction towards renewable energy. Wind turbine is one of those alternatives with a huge acceptance around the world. The growth of installation of wind turbine farms is more frequent along last years. When we talk about large projects like this, it's unavailable refers to operations and maintenance costs. This can overcome approximately the 20% of the total energy generation cost. When a wind turbine has a lot of downtime, its productivity decreases and the operation and maintenance costs increase. In contrast to that, condition monitoring systems appear as a suitable strategy since condition monitoring is applicable, even when in an offshore environment where conditions could be worse and terrible, as we know. That's why early fault detection has become a meaningful strategy to increase the competitiveness and productivity of wind turbines. On the other hand, we must introduce the concept of SCADA. Supervisory control and data acquisition systems are installed in all industrial science wind turbines. Most of the fault detection prognosis strategies use data of vibrations, for example, sounds, etc., which requires additional sensors installation. That's why we propose a methodology where we use only SCADA data to detect faults in wind turbines. These are the main features of the simulated wind turbine by FAST software, which has a product of National Renewable Energy Laboratory located at USA. In this table, we can see that characteristics like rated power, number of blades, hub height, etc., belonging to the wind turbine. In this another table, we have instead the installed sensors into the simulated wind turbine, like generated electrical power, rotor speed, generator torque, etc. As we see, we have also added a little bit of noise power in order to do the simulation more realistic. Originally, 8 faults were performed in all simulations done on the wind turbine. However, for this work, we have just selected 3 of them, which are related to pitch actuator, generator speed, and torque actuator. As of the performed simulations using FAST software, we collected data in what about we are talking about now. 260 simulations were done, and these are divided into groups. 100 simulations with healthy data and 160 simulations with faulty data. These 160 ones, 20 simulations correspond to each fault. Recall I said that originally 8 faults were taken into account. Each simulation has a temporal window of 600 seconds, as of which the first 200 seconds correspond to transient state. That's the data we don't use, while the last 400 seconds correspond to a steady state. That's the data we use instead. Recall also that the data were down sampled to a period of 1 second, with which we set the frequency like this is a SCADA system. With respect to data split, we must take into account that this is a normality model, that the algorithm is trained with only healthy data. The algorithm, which is an autoencoder, will be explained with more detail later. So, for the data split, we use 70% of healthy data for train, 20% for validation, and the last 10% for test. In this way, we complete the 100%. As we see also, the 100% of faulty data is for test, since in the test we enter both healthy data and faulty data. When we have data with different origin, magnitude order, etc., we must employ a standardization strategy in order to put all data on the same scale and don't add a certain bias to certain features. In this work, we use min-max scaler, which scales the data in a range from 0 to 1. To do this, we compute the minimum and maximum values for each column, and then we compute the scale values as we see in the equation. in order to work with the aforementioned described faults, we need to establish the next concepts: sampling time and detection time. Detection time is the elapsed time between the fault occurrence and its detection. It's related to sampling time because we have the detection time in terms of the sampling time, as we show in this slide. For example, for fault one, we see that this requires fulfilling that detection time is less 100 times sampling time. The number of times we also call J, or the number of sampling periods. In this work, to be more restrict, we selected two shorted numbers of sampling periods, which are, in this case, 3 and 10. In this slide, instead, we show the matrix transformation since originally we have a matrix with 400 columns, which represent the 400 seconds of simulation, and this matrix has 260 rows, which are the number of simulations instead. Now, considering the J value, we reshape that matrix into another matrix with J columns and many rows. So, next we have the multi-fault detection model. In this figure, we can see the application of the above matrix transformation, because that's the data reshape done for each sensor. As we can see, in this case, we observe, for example, 3 columns per sensor, which is J value equals to 3. Next, with the prepared data, we are ready to send those to the autoencoder for the training stage. In this figure, we see that the predictions of this model, which are the reconstruction basically of the input, that an autoencoder works. Between the input and output, there is a reconstruction error, as of which we said if there is a low error, probably the sample is healthy. But if the error is large, for example, probably the sample is faulty. Recall that the model was trained with only healthy data. As of the computer errors, these are displayed as a matrix. Then we have to transform these to a representative error per row or tested sample. Before continuing with the explanation, this table remains the architectures of the autoencoders for each J value. For example, we see that the numbers of neurons change and the other hyperparameters remains static. So, going back to the slide 18, we compute those errors using the red square error applied to each row or tested sample. G is the total number of columns since we have 9 sensors and 2 possible values for J. These are 3 and 10, as we said. Observing the data, we see and know that several variables make data take a sinusoidal behavior, so we cannot clearly see the trend of the data. And then it could be kind of difficult to detect a fault. Moving average appears instead as a strategy to extract the trend of a time series, computing the mean of shorter and successive time series. The presented equation in this slide computes those time series mean or average, in which we must define the temporal window or the lag. For this case, we set 30 minutes as the lag. Now, in order to detect the faults over the healthy region, we propose a matrix based on the statistics of the training errors. For example, we take the mean and add 3 times the standard deviation, so we set a threshold which defines clearly 2 regions where a sample can fall: a healthy case and a faulty case. Now we see the results and discussion finally. For example, in this figure, we present the results, and as we can see, we have 2 dashed lines which define into this figure the healthy thumb. For example, we observe that black samples are detected as healthy, and that's correct. On the other hand, we see that, for example, there are 3 well differentiated curves which are located on the healthy thumb. So these have been detected as faulty, and that's correct also. Eventually, we conclude that all samples in two scenarios, G equals to 3 and J equals to 10, were correctly detected as faulty or healthy. As of this, we can take some conclusions and we define the further work. We have some ideas. For example, with J value of 3, the prediction errors are lower, attaining a better performance with a shorter detection time. That's important. And the combination of an autoencoder with as a normality model shows being a great strategy to make multi-foul detection. The downsampling strategy is useful also in order to feed the data as if a SCADA system has generated them. It would be interesting to include data augmentation, for example, techniques in order to apply other deep learning strategies, for example, CNNs, RNNs, etc. And with that, we conclude this presentation. Thank you so much. Does anyone has any question?
Thank you for your presentation. Let's see. No questions in the chat. I will do one question. What kind of application for the manufacturer you expect in the near future from this research? Hello? Are you listening to me?
Hello. Can you repeat me the question?
What kind of application from this research you will expect to be applied from the manufacturers to develop this kind of products?
Actually, this technique you can use in any manufacturing system if you want to detect an anomaly or if you want to detect some fault in any component of the system. So you can use in any kind of manufacturing system.
Do you have any application from this research by now?
Actually, now we are actually in this research we are detecting fault in the main bearing in the high-speed shaft. We are detecting a fault in that component of the wind turbine.
Okay. Thank you. I will ask again if there are any questions from the audience. There are one question in the chat. Average data is a kind of low pass filter, LF. Why not use the LF instead?
I think the LF is a good idea. We didn't try to use it, but we use the moving average because we try to eliminate not positive, positive positive. So some values that maybe are anomalies and the system don't recognize it. Before that, because that we use the moving average and use the LF is a good idea. We can try to use it.
Thank you, Mr. Helhey from the chat, and thank you for your response, Mr. Encalada Davila. So, no more questions from the audience, no more questions in the chat. I wish you good luck to the future, and I hope to see you in the next future on the next eCorrect conference. Bye. Thank you. So you finish this section. I hope to see you on tomorrow morning. And goodbye to all. Finish from today. Thank you for your